Hey, I'm Amy Wang, and this is my Lab 5 presentation, Choose Your Own Adventure Lab. I decided to observe a maximally inelastic collision between two toy cars, one that is stationary and the other colliding into it. To stimulate maximally inelastic collision, I put tapes on the cars so they stuck together after colliding. The objective of this lab would be to quantify the maximally inelastic collision, create a computational model to replicate it, and analyze the change in momentum and energy. The result of the lab was that the computational model successfully models the experimental data, the momentum conservation principle was satisfied, and kinetic energy was lost. Although there was slight error in the computational model, most likely due to the fact that friction was not included in the model. Now let's talk about the models I used to compute this lab. There are two main ones, with the first being the momentum principle. The momentum principle in its derivative form is delta p over delta t equals F net, so the change in momentum is equal to the net force acting on an object times the duration of the interaction. This is true for a small delta t. In the case of a collision between two objects, the F net would equal 0, making the change in momentum equal 0, which is the momentum conservation principle. This principle states that the total momentum of two objects before a collision in an isolated system is equal to the total momentum of the two objects after the collision. The energy principle states that the change in energy is equal to the work plus heat. In maximally inelastic collisions, there is maximum dissipation and the objects stick together, so the final kinetic energy does not equal the initial kinetic energy. Now let's look at the video I filmed and analyzed in Tracker. As can be seen, tapes are at the heads of both cars to simulate a maximally inelastic collision. I track the center of mass of the red car, the blue car, and of both when they collide and stick together. I set the origin here at the first center of mass I tracked for the blue car. I also set a calibration stick for the Monopoly box at 4.26 meters. I put in the data I collected from the point mass collections and placed them into Excel. I then took the X and Y data for the red car and the blue car and made CSV files out of them to be put into the code later. This is a position versus time graph I made that shows the positions of the red car, blue car, and the cars together. I took the number used for this graph to calculate velocity using change in position over change in time. The blue car initially moved at 1.3 meters per second and slowed down to 0.57 meters per second after the collision. The red car, being stationary, started at 0 meters per second, but also moved to around 0.6 meters per second after the collision. The combined velocity after the collision was also 0.6 meters per second. Let's look at the code I used to create a computational model for my experimental data. These two parts of the code are to collect the X and Y data of the red car and the blue car from the CSV files created using the tracker data. It will be used to compare to the computational model later. Here I created the objects I needed to show the lab. I created two spheres for the experimental data and two for the computational model. I placed the computational model below by placing it in the y direction by -1 so they will be easier to compare when the code is run. I put in the initial conditions of the masses and velocities of the two cars here. Here I did some other initialization steps and I calculated the momentum of both cars before the collision, giving me the total initial momentum here. And here I calculate initial kinetic energy by adding the kinetic energies of the two cars before the collision using the formula 1/2 mv squared. The while loop I wrote here updates the position of the cars. This top half updates the computational model, and the bottom half takes the data from the CSV files. Now let's run the code. Note that the top shows the experimental data and the bottom shows the computational model. After the code was run, I print the final velocity of the blue car, which was about half its initial. The next thing is change in momentum, which was basically 0, so no change. The last thing was the loss in kinetic energy, which my code found to be 0.015 joules, so there is a loss of energy as initially stated. Let's look at the model again. The computational model seems to have moved faster than the experimental data, and that is most likely due to friction acting on the experimental data. The values from the computational model are a bit different from the observational data, and here's why. The initial momentum of the system for the observed data would be equal to the blue car's momentum as the red car's equals 0. The initial momentum is 0.052 kilograms meters per second. I calculated the final momentum to be 0.044 kilograms meters per second. There is a 0.008 difference, but momentum is conserved for the most part. Now let's talk about the energy principle for the observational data. Using the formula 1/2 mv squared, I found the initial kinetic energy to equal 0.0338 joules and the final kinetic energy to be 0.0133 joules. The loss in kinetic energy is 0.0205 joules. There is a difference between what I calculated and what the computational model shows because of friction and human error when I misplaced some of the point masses in tracker. Finally, let's talk about the questions. Why was this a maximally inelastic collision? What does that mean? A maximally inelastic collision is characterized by having the largest possible change in the system's internal energy such that the momentum is still conserved. It occurs when the objects stick together after the collision, just as mine did. Because the objects stick together at the end, there is one final velocity, which is what I have. Now let's talk about the second question. For my model system, was the momentum principle satisfied? The answer is yes. The initial momentum was found to be 0.052 kilograms meter per second, and the final momentum was 0.044 kilograms meter per second. There is a slight difference of 0.008 kilograms meter per second, but this is most likely just due to errors. Thanks for watching my Lab 5 presentation on maximally inelastic collision.